Bum, 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 bum. Hey, boys and girls, thank you so much for joining me once again for another lesson online. We are looking at circles, and this is one of many lessons on circles. And you can see that it's covering two different sections from your Springboard book. So if you want more resources, more problems to go try out, make sure you go and try sections 24.1 and 24.3. But these are the notes that you should have been able to download. You can follow along or you can print them out. And also the homework is going to be on a link under this same assignment for the Edpuzzle. So not in Edpuzzle, but under our assignment on MyCCA. So I'm starting you off with just the most basic definition of a circle. A set of points in a given plane that are a fixed distance from a given point called the center of the circle. And so if you are looking at a circle, and if you have your definitions from in your notebook, you can go ahead and just add the circle into your next definition. If you were not able to get back to school to grab your definitions, that's okay. You can write this on a piece of paper. That's just fine. I'm not going to be checking your notebook from here. So our circle, this circle that you see, the circumference, the outside of it is made up of a set of points, all tiny, put together, and they are a fixed distance from the center. So we always name our circles from the center. So if I gave this point P as my center, we would call this circle P, naming the circle from its center. And then the fixed distance, right? If this is PQ, that's your radius. And so all of the radii are the same exact length, right, around our circle. But Q, R, and S are just three of the points that represent points on the circle. Point P is not actually considered on the circle. It's just the center, and that helps us establish our circle points. So I've listed in here some other definitions that you should already have. But again, just in case you weren't able to go get your notebook, here they are. You should understand the radius of your circle, what a chord is. And just a little reminder, the chord just goes from a point on the circle to a point on the circle. So AB is a chord here. And the diameter is a special chord that runs through the center. So DE is your diameter. And of course, the diameter is the same as two radii put together. All right, so our main focus of this lesson is tangents. So we're going to look at that definition. Here's your definition. A tangent is a line that only touches your circle in one point, and that one point is called the point of tangency. So you can see we've got a lot going on in this picture. You have a circle with a center P, and this line, the red line AB, is only touching our circle at point A. That's its point of tangency. And so line AB or line BA is considered tangent to circle C. And so we're going to look at two different theorems. There are two theorems, and all of the work that you do for these two sections are going to come from these two theorems and your understanding of these two theorems. So if you have your theorem paper, you can go ahead and write this down as your next theorem. Tangent to a circle theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle. And so notice, you guys should notice that biconditional wording, if and only if. That means that there is the original conditional statement and the converse is going to be true all the time. And so we're going to use this picture right above that I have here in the notes to demonstrate what this theorem is talking about. So let's take it the first way. If a line is tangent to a circle, then it is perpendicular to the radius of a circle. So we could say the first way, let me move this up just a little bit. So the first way that we could look at this is if line AB is tangent to circle C, then we can say that CA, the radius, is perpendicular to AB. And so what's happening is that you can draw from your radius, your center, to the point it's in tangency, and you've got a perpendicular relationship. Now, on the flip side, we can turn this whole statement around and look at the converse, and the converse will also be true. So the second thing that we know is true is that if CA is perpendicular to AB, then AB is tangent to circle C. All right, so they have this back and forth relationship. There's always going to be a radius perpendicular to a tangent line, and a tangent line will always be perpendicular to the radius. And so you're going to see a couple of different problems to work on. As you might have guessed, when we have perpendicular lines, there's always, right, an opportunity. If we were to connect CB and you look at this, we've got a right triangle. So Pythagorean theorem could come into play. We could have trig functions come into play because we've got right triangles. So all of those things, they're 1690s, right? All of those wonderful things that you've already learned about can come into play. Here's what some of your problems are going to look like. And I made the first one kind of easy. It just wants you to identify if AB is actually tangent to this circle. And so you're going to use the converse of the Pythagorean theorem, right? You guys will know if AB is perpendicular to BC, if that is indeed a right triangle. Now, I hope you're looking at number one and you're saying, yes, I can tell that's a right triangle because I recognize the triple, right? When we divide the 8, the 6, and the 10 by 2, right? We can divide these by 2 and we get a 4, a 3, and a 5. So this is a 3, 4, 5 right triangle. Now, if you did not see that, you're going to use the Pythagorean theorem. You're going to ask yourself, is C squared equal to A squared plus B squared? You want to check that out. And then your hypotenuse here would be the 10. Or you could put the 5 in to make it easier. And then the 8 and the 6. So 10 squared is 100, 8 squared is 64, and 6 squared is 36. And this does indeed give you a right triangle. So this is the work that you need to prove it. It's just using the converse of the Pythagorean theorem. And you've got a right angle here. So this indeed is a big old yes. Is AB tangent to circle C? Yes, it is, and we've got the work to prove it. So why don't you go ahead and try number 2? All right, So number two, hopefully you said this is a big no. And if you wanted to, you could go ahead and reduce. These numbers are small enough. I'm going to leave them the way they are. So we're looking at what would maybe be our hypotenuse is 9. I'm going to do this one over here. Right? And we want to see if this equals 4 squared plus 6 squared. So we have 81 equals 16 plus 36. And 16 plus 36 is a 52. So that does not equal, right? That's an obtuse triangle. That is not a right angle. So is tangent AB, is AB a tangent to circle C? We would definitely say no, it is not. All right, so that's one type of problem you're going to see is just evaluating whether or not you have a tangent going from this theorem. From this theorem, you might also get problems that look like this. Moving on in the notes to number 3. Number 3, I've given you 2, and I'm going to do the first one with you. If AB is tangent, so now they're telling us that AB is indeed tangent to the circle, and we're going to find the value of the missing variable. Now, here's what's interesting. They've used R in both of these. I like these to start. They don't always do that, but those are the radii of your circle, and they should always be the same length. So with Pythagorean theorem, you're going to have, using c squared equals a squared plus b squared, you're going to have r plus 2 quantity squared equals 4 squared plus r squared. Now, this is an interesting problem, and most students, even in pre-calculus, there's probably about 10% that would do this wrong. So don't be one of those people. But r plus 2 quantity squared is really r plus 2 times r plus 2. If you can understand that every single time, you'll be on top, because that's a good thing to know. So we're going to do r times r is r squared. We have r times 2 is 2r. We have r times 2 is 2r plus 4 equals 16 plus r squared. Now, these problems, some of them, depending on where the variable is, can be a little bit more difficult, but this one's not that bad. Do you notice that you have an r squared on the left and an r squared on the right? So when you go to reduce them, they should cancel out. That's right. So these are going to cancel out. You are left with 4r plus 4 equals 16. So 4r is going to equal 12, and r will equal 3. Not bad. I'm going to give you a moment to go ahead and try B on your own. All right, let's take a look at B. Hopefully you just followed what we did in this one because it's very, very similar. We know that CA is our hypotenuse, so that's going to be r plus 8 quantity squared equals 12 squared plus r squared. So r squared plus 8 is going to be r plus 8 times r plus 8. And when we put this together, we're going to get r squared plus 8r plus 8r plus 64 equals 144 plus r squared. And again, the same thing is happening that happened in the last problem. The r squareds are canceling. We get 16r plus 64 equals 144. Subtract the 64 from both sides. 16r equals 80, and r will equal 5. Did you get that one? There will be some in your homework, so you'll get to practice those some more. All right, so that's the second type of problem that you're going to encounter. So 2 different types of problem from that one theorem. And another thing that you're going to see and look at are just different ways that these lines of tangency can be represented. So sometimes circles have common tangents, and this is called an external one because they're not in between them. And this one is going in between the two circles, so it's an internal tangent. And then I've just given you some different ways that you can see this play out. So these two circles have quite a few different common tangents. These ones only 3, these only 2, these only 1, and then these are concentric circles. We looked at those at the beginning of the year, no common tangents. So just a little heads up for some things that you might look for when dealing with tangents and common tangents. All right, so our last theorem that we're going to look at has to do with congruent tangents. And I like to call this theorem the ice cream cone theorem. It states if two segments from the same exterior point, here is the same exterior point, and here are two segments, AB and CB, are tangent to a circle, then they are congruent. So as long as I know that point A is tangent to the circle and point C is a point of tangency, then I know that this is true, right? That these segments are congruent to one another. Now, here's the cool thing is that when you look at these, watch what happens when I draw in, right? If this is point A right here, and I know it makes that right angle, yes, and this is a radius, and then point C is somewhere right here. I'm just drawing these in by hand. So I know it's perpendicular to CB, and I draw it in the radius. What kind of quadrilateral did I just create? That's right, it's a kite. And also it's a quadrilateral. How many degrees are inside a quadrilateral? Hopefully you said 360. So you can see that there's a lot going on here to play around with. If I wanted to, I could draw in a third segment and I could bisect that kite right down the middle and have two congruent right triangles. So everything is just kind of coming back around here. But don't forget, 2 points of tangency that meet an external common point are going to be congruent segments. It looks like an ice cream cone. Maybe this one looks like a bird's beak, but I call this the ice cream cone theorem. So they have some fun problems to look at. Let's go look at 2 that I picked out for our notes. Here's number 4. So if segment AB and segment BC are tangent to the circle, so when they tell you that they're tangent, you're putting the theorem into place, you know that these are congruent to each other. Can you take a moment to go find the value of x? Right, so if they're congruent to each other, hopefully you know that AB equals BC, right? Congruent segments have equal measures. And we're going to plug in AB as x plus 15, and BC is 2x minus 15. We'll subtract the x. We will add the 5. Oh my goodness, Mrs. McGuire. I made that a 15. That's actually a 5. Oopsie daisy, that would have changed the answer. All right, so let's add the 5. And x is equal to 20. And you can plug that in and make sure that it works, right? What's 20 plus 15 is 35, and 2 times 20 minus 5 is 40 minus 5, which is 35 as well. So you can tell that your x is working. Both segments are 35 units apiece. All right, this is one of my favorite types. I love that they do this. Number 5. Triangle GEF is circumscribed about the circle A. And we've talked about circumscribed circles. The triangle is circumscribed. This circle is inscribed, the triangle, but we know it's touching at one point. So we know if it's touching at these points that these are all tangent segments. So we have this theorem working a couple of times, right? Point E gives us these two segments that are congruent. So I don't have a point here. I wish I had this labeled. But this segment is 4, so that means this segment is 4. Coming down here, We have from G a length of 13. That means this length would also have to be 13. And then we've got, let's see, from this point of tangent C to F is 9. So from F to here is also 9. And then it says find the perimeter. Go do it. All right, so looking at the perimeter, let's see, we have 4 plus 4 is 8, 9 plus 9 is 18, 13 plus 13 is 26, 16 and 6 is 22, and we have 52 units around that perimeter of the triangle. All right, go get your worksheet and work on this. If you need help, come to Extra Help this week. Bye-bye.